I welcome you all for this wind energy harvesting session. So, we'll start with the fundamentals of the wind energy harvesting. Basically, wind energy is nothing but the energy which is caused by the wind and that is actually extracted by the wind turbines. So, it can be classified with wind turbine siting and power curves, wind turbine power, likewise. So, we'll see one by one. So the wind turbine siting is nothing but wind turbines can be grid connected or independently operated from isolated location based on the wind energy availability. So the two main critical factors in finding the most suitable location for the wind turbines are the wind speed and the quality of the wind. So this decides whether the place is suitable for the wind turbine. So this information provides the wind losses. The most suitable sites for wind turbines are turbulence-free locations because turbulence makes the wind turbines less efficient and also affects the overall stability of the turbine. So the wind turbulence is influenced by the surface of the earth. So depending on the roughness of the terrain or the place, the wind can be more or less turbulent. So it is about 3000 feet and above ground level that the wind is not affected by the friction against the earth surface and therefore there is no turbulence at all at that particular place. So wind power can be categorized into 7 different classes according to the wind speed, which is measured in meter per second, and also the wind power density, which is in watts per meter square. So these are the different classes, 7 different classes available at different heights, okay, and the power at a particular height of 10 meters and 50 meters and corresponding wind power and wind speed. This is found from a research paper, okay. So these wind power classes are shown in the table, which is actually noted that the wind power class corresponds to 2 power densities. Yes or no? We have 2 power densities. So for example, wind power of class 4, see here, represents to wind power density of range of 200 as well as 250 watts per meter square. So it is from 3 to 4 as well as 4 to 5. Likewise, 2 to 3 and 3 to 4, which means class 3 can have 2 wind power densities. Okay. So wind power classes are found with this, and wind power classes corresponding to the wind power density and wind speed is based on the wind height at which it is placed. So the wind map actually provides useful information about the classes in different geographical places based on the wind's annual average speed and power. The wind power classes are determined for the specific location and those wind classes are indicated on wind maps. So this is only for that particular location. Again, if you move on to some other location, we have to find the annual average speed and power, and then we have to calculate the wind power classes for that particular specific location. Okay, these maps also provide the information regarding the wind's potential at specific location, and this can be used for the wind turbine siting determines where it can be sited, or like based on the power classes and the power density, we can conclude whether it can be important, whether it is a suitable place to locate it or not. Another important factor for the wind turbine siting is the roughness of the terrain. So like this wind power classes or the wind power density, roughness of the terrain is also one important factor which decides the uh, wind turbine siting. Let's see that also. So there are roughness classes we can see here in the table 2.3. So which explains the relationship between the wind speeds and the landscape. Okay. So the roughness class varies from 0 to 4, where class 0 represents the water surface and the open terrains with surface areas, and class 4 represents the very large cities with tall buildings and skyscrapers, which means possibility of getting the wind is less. Okay. So two key parameters regarding the different geographical locations affecting the wind turbine siting are nothing but the friction coefficient and the roughness classification. So there is one more point that we have to concentrate, which is nothing but the friction coefficient, which is shown here. So this is about the roughness classes. See, class 0, roughness class 0 represents the water surface and corresponding roughness length. Likewise, for the class 1, it is representing the open area with few windbreaks, and the corresponding roughness length is this. Whereas for the class 2, it is the farmland with some windbreaks more than 1 kilometer apart, and so the roughness length is 0.1. Whereas for the roughness class 3, it is from there the urban class starts. So urban districts and farmland with the windbreaks of many windbreaks. So the roughness class is 0.4, length is 0.4, and for the last one, roughness class 4, it represents the dense urban or forest. So the roughness class is 1.6 correspondingly. So this tells that how far the roughness will be and the relationship between the wind speed and the landscape, that decides the roughness also. Likewise, when we go on to the friction coefficient, this friction coefficient is based on different terrain characteristics, and that's what is shown here, corresponding friction coefficient with the terrain characteristics. So when the terrain is smooth, hard ground, calm weather, then the friction coefficient is 0.1. Whereas when it is large city with tall buildings, then the friction coefficient is 0.4. Whereas if it is tall grass or level ground, it is 0.15, and high copse, hedges and shrubs are there, then particular terrain will have a friction coefficient of 0.2. Likewise, if we have a wooded countryside with many trees over there, then it is 0.25. Whereas if it is a small town with trees and shrubs, then the wind, corresponding friction coefficient is 0.3. So this all decides the particular wind turbine siting. So before we fix a location, we have to decide on we have to go on with, this particular places, how roughness classes and the power class, wind power density, and then the friction coefficient also. So this is nothing but the wind speed rate at which respect to the friction coefficient. So this tells the equations. With this, we can even find that the wind speed, we can conclude that wind speed increases exponentially with the altitude. Of course, that we know, right? Therefore, the speed of the wind at 10 meter will be totally different from its speed at the 100 and 200-meter height. So, of course, we have to decide upon the height also. That is what we try to conclude with the calculation based on the roughness length, height above the ground level, and the velocity, corresponding velocity also, wind speed with the wind speed. Okay. So this is from that equation, it is observed that the ideal wind turbine site is a location with smooth wind, constant speed, and without turbulence, which is only possible in locations with roughness class 0. So we conclude that it is all possible with the roughness class 0 location, terrain location. As mentioned, the roughness class 0 represents the water surface and open terrains with smooth surface, where wind speeds are constant and there is no turbulence because there are no obstacles, there is no wind break at all. Okay, so due to this very low roughness, the wind speed at 30 meter above the water surface is not different from its speed from the 50-meter height. Same, almost, they conclude that it is almost same because there is no much wind break. Due to this low turbulence, the lifetime of the turbine will be more, and also there are great variations in the wind speed and direction. Though there are great variations in the wind speed and direction, depending on the weather conditions and the local surface conditions, with the great variations happening during the daytime, there can be, of course, the variations in the wind speed and the direction also. Because of this low turbulence, almost lots and lots of wind turbines are situated in the offshore in sites above about 5 to 10 kilometers in the sea level, in the sea. So wind shade does not affect the wind turbines that are far in the sea. Therefore, based on this siting, there are two main types of wind turbines, onshore and offshore. Onshore is nothing but site on the land, which is nothing but wind turbine on the land surface, whereas offshore is nothing but the wind turbine or the site is on the sea, is in the sea. Okay. So the generated electricity from the onshore wind turbines can be transferred and connected to the grid through transmission lines. That's easy to do. But offshore, it's like exposed to less turbulent winds. Of course, no wind shades. However, it is difficult to transmit the power. Transmission lines cannot be placed there in the mid of the sea. So transmission power transmission is a bit difficult. Next comes the wind turbine power. So the wind turbine power is actually calculated based on three things. One is Betts law, power curve, and the power coefficient. So Betts law actually demonstrates the theoretical maximum power that can be extracted from the wind. So this helps us to find the maximum power that can be extracted. So the extracted energy is actually from the kinetic energy of the wind. So higher the wind speed result in the higher extracted energy. So it should be noted that the wind speed after passing through the turbine is much lower than before reaching the turbine, before energy is extracted. So this means there are two wind speeds, one before the wind approaches the turbine and other after the turbine. So it's like before hitting the turbine and after hitting the turbine. So there can be two different speeds. So this figure shows that both speeds of the wind after the turbine and the wind has after it is actually decreasing. So that's what is actually represented. So the decreased wind speed after the turbine provides the information about how much amount of possible energy can be extracted from the wind. That is what the main thing is. So the Betts law actually tells us that there are two types of energy, two types of wind energy, one before hitting the turbine and other one is the after hitting the turbine. So after hitting the turbine, the energy is decreased, and this energy or the decreased wind speed is what is providing the information for us to calculate or check what is the possible amount of energy that can be extracted from the wind. That's very important. So moving on to the power curve, it's the diagram which represents the relationship between the speed and the power, okay, which is important for the turbine design. Fine. So power curves can be, it's made up of series of measurements for one turbine with different speeds. This is done to obtain the accurate power curves. So the wind should be non-turbulent, and there is cut-in and cut-out wind speeds that can be found from the power curve. So the cut-in shows the minimum power wind speed needed to start the turbine, whereas the cut-out represents the speed point where the turbine should stop rotating due to the potential damage that can be done. Means if the wind speed increases beyond that, then obviously there might be a damage. So we have to calculate that. The power curve, can be divided into few regions. These regions are nothing but, these regions are represented in the figure here, like cut-in, they're separated by cut-in, nominal, and wind cutout speeds of wind speeds. So once the rotor, starts spinning, it can be assumed that the amount of produced output is linearly increasing with the speed. See, it is increasing. We assume it in such a way that after reaching a particular speed, reaches the nominal speed for which the turbine is designed, the output power remains relatively constant. However, an increase in output power above the nominal value might damage the system. So we have to maintain such a way that the power is in the nominal range. It is not increasing beyond that. Therefore, even in spite of the change in the wind speed, means even if the wind speed is increasing, the speed of the turbine should be controlled so that it is constant. To be maintained, it should be maintained constant. So this is achievable, or this is achieved using several controlling parameters or techniques such as pitch angle control or controlling the load of the turbine. So after the wind reaches the cutout speed here, in order to protect the system from any kind of damage, the turbine should be stopped by setting the pitch angle such a way that it does not face the upcoming wind. So usually at very high speeds, the stability of the blades and cables is weak. Thus, the system should immediately stop. So this is how we try to plot the curve, which is nothing but the relationship, power curve relationship between the speed and power, which tells us the information that once the rotor starts, or from the cut-in wind speed or the initial speed, it starts increasing, power starts increasing. And after the nominal wind speed, the power is maintained constant. So after this particular range of speed, the wind speed should be maintained constant. Though there can be an increase in the wind speed, we are expecting, or we should provide some control techniques to control the wind speed such a way that it is maintained in the constant wind speed to produce the same constant power. And at the cut-out wind speed, in order to protect the entire system, we try to cut off, or we try to stop the wind turbine. So the next parameter is the power coefficient. Power coefficient is nothing but the ratio of the electrical output power or of the wind turbine to the total potential of the wind power. This depends on the wind speed, of course. So the power coefficient curve is shown in the figure 1. I'll show that. And also it can be observed that both the figures provides the maximum have a maximum curves have a maximum for the same wind speed. So hence the power coefficient curve always have a maximum point for maximum possible turbine power. This is usually for the this is usual for the most frequent wind speeds. So this is nothing but the equation representing the power, total power. This is the curve, power coefficient curve for a wind turbine. So this is speed versus power coefficient, and this is the total power, extracted power versus the speed. So this helps us to understand or observe that the power coefficient depends on the specific design of the wind turbine. And also each wind turbine has its own power coefficient that depends mainly on the top speed ratio. So in addition, the power coefficient depends on the pitch angle, which is defined as the angle between the blade surface and the plane of the wind rotor, which is actually shown here. This angle represents that. For onshore, there is a great difference between onshore and offshore wind turbine power coefficient. So for onshore coefficients, onshore turbines, for example, the blades are designed such that the optimal tip speed is limited to roughly 50 to 70 meter per second, because the blade tips cause excessive acoustical noise and can cause damage at higher speeds. Whereas on the other hand, the noise does not play an important role in offshore turbines, and higher speeds lead to slightly higher optimal values of the power coefficient. So this is about the wind turbines basic fundamental ideology. All these are very important for wind power siting, as well as the extraction of energy, wind energy from the wind turbine. Thank you.